my name is Xiao. I'm an engineering manager at Airbnb. Alongside with me is Toby. He's a senior staff engineer at Airbnb. So today we're going to talk about Airbnb's metrics platform, Minova. Last year, we actually published 3 blog posts about Minova. But since then, we have made major architectural changes to the platform. So today, this presentation, we're going to be mostly focusing on Minova 2.0. If you are interested in learning more about Minova 1, feel free to read our stories in Airbnb Tech Blog. All right. So here's the agenda. So to provide some context, I will start with Airbnb's data journey and then reflect on some of the growing pains that we experienced. And then I will cover how we created Minova to solve those pain points. Toby will talk about the major challenges Minova 1.0 faced and what we are doing to address those pain points in Minova 2.0. And of course, we will leave some time in the end for Q&A. Airbnb, like many other startups, Airbnb had a humble start at the beginning of its data journey. In early days, we had only one full-time analyst working on data. And we did not have enough resources to build a proper data warehouse. So his laptop was effectively our data warehouse. Right? At that time, queries were run against production databases and sometimes caused trouble that affected the performance and availability of Airbnb.com. On the plus side, data, even with such a limited investment, data still helped us identify many growth opportunities. So as Airbnb gained traction, so we brought in many more data scientists and data engineers. We started building our own data infrastructure and data products. So for example, we built an open source Airflow and also Superset. We created our internal data catalog, data portal service, as well as A/B testing platform to democratize data. So with a much more mature data infrastructure, more tables, more pipelines got created at an exponential rate. And very soon, growing pains started to manifest. Okay, there was a time when Brian, our CEO, asked a simple question. Which city had the most number of bookings in the previous week? Guess what? 2 teams, data science and finance, came up with different numbers. Why? Because they read from different tables. They had different business logic in their metrics computation pipeline, right? Very familiar story. But anyway, such inconsistency issues actually hurt our confidence and trust in data, right? And even teams started second-guess their own data eventually. So what caused those issues in the first place? Initially, data scientists created a core set of normalized tables as the foundation of analytics. That is actually a really good practice. However, more and more denormalized tables got added on top of those core tables, right? And many people actually keep reinventing the wheels because they didn't know that similar tables or pipelines may already existed to answer their question. Just keep doing that. And over time, the proliferation grew to a point where the tables became tribal knowledge, and the data lineage was too difficult to track. Right? So when issues were discovered and fixed in the upstream tables, there's no guarantee those fixes would propagate to the downstream tables or pipelines, right? We ended up with a messy data ecosystem that is very hard to maintain. So to save our data lake from becoming a data swamp, we started like we analyzed all of the pain points and started to imagine not ideal world. What if we had a single source of truth for metrics and dimensions? How could we leverage automation and governance to ensure data quality? As we explored answers to those key questions, we created Minova. So what exactly does Minova do, right? Simply put, it manages the full life cycle of metrics and the dimensions. Under the hood, Minova has a centralized GitHub repository to host metrics definitions and the dimension definitions. Right? Anyone at the company can view, create, and update any metric, right? But these changes do need to be reviewed and tested before getting merged into the repo. We also leverage Airflow for DAG orchestration. We have built-in data checks to ensure data quality, and our pipeline would self-recover after failures caused by transient issues. Right? All of the downstream applications, they access Minova metrics through a unified set of APIs, whether it's dashboarding tools such as Superset, Tableau, our internal A/B testing platform or anomaly detection platform. They all access the same set of Minova datasets. When there are major changes that needs to be made on those dimensions or metrics, Minova actually offers flexible options to automate the backfill jobs. And of course, we have data management and retention features that allows us to meet GDPR requirements or reduce the cost of Minova. So prior to Minova, users had to go through many steps in order to get insights out of data, right? And some of the steps are complex and very time-consuming, right? For example, testing Airflow jobs, backfilling data, validating data, just to name a few, right? So with Minova, many of those complexities are abstracted away. So the users only need to focus on defining, metrics, like really focus on just the business logic, right? They don't have to worry about, creating data pipeline jobs, etc., right? So, all right. With this unprecedented convenience, we have seen accelerated adoption of Minova in the company. So when we, even just comparing to last year, so the number of metrics has more than doubled. So when we published our blog post last year, we reported 12,000 metrics and 4,000 dimensions, right? Looking at the number now, so we are seeing 30K metrics and 7,000 dimensions. So very clearly, Minova has been a great success at Airbnb. And however, having said that, right, so Minova does have a lot of challenges, right, face a lot of challenges. So I'm going to pass on to Toby to talk about those challenges next.
All right, thanks, Xiao. So as Xiao said, Minerva has been a game changer for Airbnb, right? With Minerva, we can scalably compute thousands of metrics and move petabytes of data around every day, right? But at its core, Minerva was a pre-computation engine, right? You can simply view Minerva as a way to denormalize and transform data and ingest it into Druid so that dashboards and users can query and look at metrics quickly, right? So really quickly looking at this diagram, a dimension source is something like countries or devices, right? Something that you would filter on or segment. And a measure source are things like facts, right? Maybe searches or people who have booked, right? And in order to make sense of that data, Druid needs to be able to get them all together, right? So we denormalize them, basically join together the measure sources with the dimensions so they can easily be ingested into Druid, right? So Minerva does a lot of pre-computation. So when we denormalize metrics in Minerva, a very common view of metrics are things like bookings in France, right? For example, I want to see how many people booked in France. Something that's more complicated might be things like, I want to know how many bookings we had from people who have booked before, or how many bookings we've had for people who have booked in a listing with more than 4 bedrooms, right? So they can be pretty complex. So Minerva does a really good job of understanding which dimensions need to be joined to each measure, and then automating that kind of query and automating the Airflow DAGs to orchestrate materializing all these tables so that they can be ingested into Druid. One of the reasons why we needed to denormalize everything is because Druid doesn't have the best join support, right? It can only support broadcast joins, so meaning the right-hand side or the dimensions need to fit in memory. So if a dimension doesn't fit in memory, then Druid wouldn't be able to join. And so in that sense, we always denormalize in current Minerva 1.0. Additionally, Airbnb has taken advantage of Druid's roll-up features, right? So rolling up or cubing or preaggregation is basically for every dimension that you care about. For example, if you care about which country someone booked in and on which device, and perhaps on how many bedrooms, Druid, using the rollup features, would automatically, for every combination of those, kind of pre-compute those metrics. Now, this is quite fast at query time because kind of everything's already done. But one of the challenges here is that everything is, if you have a lot of dimensions or something that's high cardinality, it's kind of exponential in computation costs, right? So it can be very expensive. So what are the challenges with these kind of pre-computation, denormalization, and cubing or rolling up, right? Well, first of all, pre-computation is very inflexible, right? When you are doing some kind of analysis, you have to know ahead of time, if you want to filter something, what you're filtering on, or if you're looking at something, it has to be pre-computed, right? So, and we all know that a lot of times analysis is very exploratory, and so you might not always know what you're looking at ahead of time. And so if something isn't already pre-computed or already part of Minerva, you have to add it to the system, and you might have to wait a couple hours or even a couple of days for everything to be backfilled and consistent, right? Because one of Minerva's core tenets is to be consistent so that people are getting the right numbers, right? And so waiting for a backfill takes both money and time. And so sometimes people are in a crunch, right? And instead of waiting for the backfill, they might get frustrated. And so they might write the query from scratch, right? Effectively bypassing the source of truth. Why wait for a couple hours or a couple days when I can kind of just write my own query, which may or may not be correct, right? And so we really want to avoid that. Another part about pre-computation is that it's very expensive, right? Because what ends up happening is because you don't know what you want, you kind of ask for everything ahead of time, just in case you might need it in the future. But what ends up happening is 99% of the pre-computed data doesn't really get used, right? And so what ended up happening in Minerva is that there are many, many variants of the same metrics, right? We have bookings in China, bookings in France, bookings with 3 rooms, bookings with 4 rooms, etc., right? Because just in case you need to know that specific cut, you need to kind of predefine it. Additionally, with denormalization, because it's exponential in cost, you can't just put all of your dimensions into one table and then roll them all up, right? You need to have subsets of your denormalized tables so that Druid can sustainably pre-compute everything together, right? And so you might have a denormalized measure source with country and device, and then I might have one with country and the number of rooms, right? There's a lot of duplication there, which is very wasteful. And so, as you know, it's a lot easier for people to add things than to remove them. So over time, Minerva continues to grow. More metrics and more dimensions get added. And even though we have governance rules and cleaning up of data, of unused metrics, the growth of metrics increases, which means our cost and maintenance also increase. So how did we address these issues? So we took the time, and Minerva, as I said, has been very, very valuable to Airbnb. And so we really wanted to take what we've learned and make it even better. And so with Minerva 2.0, it was really a ground-up design from now that we know kind of how people use Minerva and what they need and what the challenges are, how can we design it in a way such that it's going to be much better for everybody, right? And so we really focused on giving users flexibility without sacrificing performance. And so we did that by introducing two main features, which is on-the-fly joins and on-the-fly aggregation, which means that we don't need to rely on pre-aggregation anymore. However, due to the constraints of big data, right, and moving data around, joining and aggregations is expensive, right? And so we also provide an optional path towards the old style of doing things, which is denormalizing and cubing, right? So if there is some kind of dashboard or use case that requires extremely fast latency and cost is not an issue, we continue to provide that option for our users. So this new architectural diagram highlights two key differences here. One is that we've moved away from Druid to StarRocks, and the other is that now we ingest not only the denormalized measures, but also the raw dimensions and measure sources. So the reason why we've moved away from Druid to StarRocks is because StarRocks, is an MPP platform, a massively parallel processing engine that really focuses on running full queries on raw events, right? So it can do things like joining large data sets in interactive time, and it can even aggregate raw data in similar amounts of time to Druid pre-aggregated queries, right? And so some of the technologies that StarRocks provides in order to do this are things like co-location, so that we don't have to shuffle data around when we join, and also a cost-based optimizer, right? When you're joining many dimensions to a measure source, the order in which those joins happen could greatly affect the query time, right? Because if you have a join that's very has low cardinality after the join, you might want to do that first before the other joins. So StarRocks automates all of that for us so that users downstream don't have to know how to manually order their queries. Another way to look at this architectural diagram is that we've shifted from Minerva being a Druid ingestion tool, right, which is kind of very specific, into a SQL generation tool, right? So Minerva now isn't focused on solely ingesting Druid, but it generates kind of advanced and generic SQL such that we can now query either in StarRocks, or if we want, and it's not ingestion to StarRocks yet, we could continue to query data using Presto or Spark in S3. And additionally, if you want to continue using Druid, we can still continue to support Druid. So how do users query Minerva in Minerva 2.0? In Minerva 1.0, the interface was a JSON REST API, right? That worked well for certain use cases, but we wanted to switch to SQL for two reasons. One is that, first of all, as you guys know, SQL is a very common language for data, and it's kind of the de facto tool, right? So we wanted users to be comfortable with using Minerva. Additionally, many BI tools already talk SQL, right? So if you use Tableau, for example, Tableau can hook up to any SQL engine and execute queries. And so by providing a SQL interface that can natively connect to Tableau, for example, then we immediately get access to all of Tableau's visualization tools. So as an example, the client might send a query something like, I want to know how many bookings in France over the number of iOS searchers grouped by the date, right? So under the hood, we've, using Minerva, have implemented the MySQL wire protocol, right? So anyone who speaks MySQL can actually speak to Minerva. We intercept that query, and then we expand that out into the normalized section here, as you see. We can take the table stays reservations. We can then join it on countries, and then we can group by on the date. And then we can also take the searches and then group that by the date and then join them together, right? So all of this is kind of done under the hood in the Minerva engine. Additionally, because we're not just tied to that, and maybe you want to go all the way to the raw data, you can even specify to Minerva, I want to do the query all the way from the source, not after the ETL step, but all the way from the source. So this provides ultimate flexibility for the user. So in order to support SQL not just for querying, but also for users to input their metric definitions in pure SQL, we needed the capability to understand what the user was asking for, right? And so we developed a Python framework called SQL Glot, which is a full Python parser and transpiler that can take in SQL queries and then run them in a variety of engines, right? The data ecosystem is very fragmented. There's many different data engines out there that understand SQL, but a slight differences in SQL, right? Hive, Spark, Trino, Snowflake, Druid, they're all SQL, but they're all slightly different. And so this is problematic, right? Because if a user types Hive SQL, but they want to run it in Presto, it might not be compatible. So as you can see in this example, using SQL Glot, we can take a Hive SQL query, right? It's using many specific UDFs like percentile and get JSON object and even a date format, right, into the special Hive date syntax. It even has a lateral view explode. Running this in Presto, you can see in the bottom here that it does its best trying to translate it over. First of all, it notices that you're using an array index, and Presto's array offset is actually 1 and not 0. It doesn't support exact quantiles, so it switches it to prox, warning you that it's done so. And additionally, it's done things like switching the time format into the Presto-specific time format. And finally, you can even see that it's moved the lateral view explode into a cross join on nest. You can even see that if you just want the AST of the SQL, you can get that all from the framework. And so this really allows us to treat SQL as a first-class citizen and making sure that we aren't tied to a single engine. So anyone that speaks SQL is now a target for Minerva. Additionally, we have many different types of users who are using Minerva, right? For example, if you're using a BI tool like Tableau or Superset, you're looking to get results really quickly. You want to hit a filter and you want to see the results instantly. Or if you're a data scientist and you're using a notebook, you might not need that second interactivity, but you want to run really complex queries, or you want to pull in a lot of user level data so you can run a machine learning model. And so with Minerva 2.0, because everyone who can speak MySQL can also speak to Minerva, we simply route it and understand kind of who's using us and what requirements they're looking for. So for the interactive use cases like Tableau and Superset, we can check star rocks to see that it's ingested, and then we can serve the fastest experience for them. So if the user has chosen to pre-aggregate or denormalize those metrics, we'll service them, and it'll be very fast. And if not, we might do a on-the-fly join. For data scientists, we'll detect that they don't want aggregated data, right? They might want all the users or visitors for a particular analysis. And then so we'll route that to either Spark or Presto so that we can return their data in a robust manner, right? So we have a query router now that can abstract the queries to the right engine depending on their use case. So now that Minerva doesn't just read from aggregated data from Druid, right? It can now generate SQL. It allows us to expand Minerva into much more advanced territory. So for example, in experimentation is very different from just business analytics, right? In business analytics, you might ask the question, how many bookings did we have in the last day? Or maybe you might ask, for all the countries that we surface, how many bookings did they have, right? In experimentation, you need to have much more robust statistics, right? And so you need to say, in an experiment, for users who have received the treatment, we need to first aggregate per randomization unit, right? So usually per user. And then on top of that, we need to find the average treatment effect of those users in their group, right? So it's a much more complicated query. Using Minerva, all this is seamless, right? We can just generate this complex SQL, run it, and give it to the user, which they can then analyze using advanced statistical models, right? So we support double aggregation. We even support on-demand covariate generation, right? So for example, in experimentation, you might want to normalize users depending on their pre-experiment activity, right? For example, if a user was a heavy booker before, they may be a heavy booker in the experiment as well, right? And so we want to take that into consideration. So with Minerva, you can just say, I want bookings for this experiment, and I want to use a pre-experiment covariate on searches and bookers so that we can then kind of normalize this out and get reduce the variance of our analysis. Additionally, because we can now get subject level data with these covariates, we can move into advanced spaces like double machine learning and even non-parametric models like sequential quantiles. One more exciting space that we've taken Minerva to recently is in the real-time metrics space. So at Airbnb, we deploy often, and we want to make sure that we're always delivering the best experience to our users. We don't want to have any crashes, and we don't want to make the experience worse for anybody, right? And so we want the ability to deploy and to be able to monitor them in real time, and even have things like automated rollbacks in case we've made a mistake, right? When we measure whether or not a deploy is successful or not, we really want to use the same metrics that the business cares about, right? There are tools out there like Datadog that provide telemetry, but those tools really work on, kind of overall data that's really aggregated and using estimators, right? And they don't have things like double aggregation. So many of our metrics can be very skewed, right? If you have a power user or, for example, a bot, and they are searching all the time or crawling, they could really skew metrics if you don't take them into account. And so with the ability to do something like subject level aggregation, or instead of asking, for example, how many crashes did we have overall, or how many users did we have with a crash, right? It's a very different question, and it gives us much more stability in our detection, right? And so with Minerva 2.0, we've integrated it into a near real-time metrics pipeline where we can take real-time data from Kafka, stream that into Flink to extract that into kind of a measure source. And then using DuckDB, we pull that in, we run the exact same business logic computing our metrics, and then use our causal models to understand if there was a shift or not, giving us confidence in our deploys. And so here's a kind of a spreadsheet of the differences between 2.0 and 1.0. But the main thing to note is that now 2.0 really has moved us away from just an ingestion tool and into a SQL generator, right? We treat SQL as a first-class citizen. We can understand it, we can parse it, we can transpile it, and we can do a lot more things with it now, right? And so Minerva 2.0 has given us flexibility without sacrificing performance. All right, and so what's next? Well, as you can see, Minerva now gives us a way to very effectively and easily get us consistent data that we can trust, right? And so based on that, now using Minerva, we can build a lot of different tooling that leverages it. For example, building and enabling anomaly detection on the metrics that we're computing every day is trivial, right? And additionally, we are looking to make the experience of contributing to Minerva and maintaining it much easier. And so we're looking into building what we're calling Minerva Studio, which is a dedicated UI for Minerva. Right now it's Git-based, but we'd like it to kind of be a full-fledged user experience. And then finally, we're looking to open source Minerva. So over the course of this year, we are looking to really improve documentation and making sure that Minerva works outside of Airbnb. All right, and here's a list of all the contributors. Minerva has been a great team effort, and thanks for your time.